Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering, and we'll continue related to modulus of elasticity. So previously we have discussed two modulus of elasticity, the Young's modulus for length and the bulk modulus for volume. So in this video we are going to discuss about another proportionality constant, modulus of elasticity, which is the modulus of rigidity, shear modulus, which is related to bending angle. So just a quick review. So basically it establishes the stress and strain relationship. So stress is basically the internal reaction force on a material to the externally applied deforming force. Let's say an externally applied deforming force is acting on a cross-sectional area of a material. There will be an internal reaction force of same magnitude but in the opposite direction. So that reaction force per unit area gives us the stress, okay, as they're equal in magnitude. So if you write applied force or reaction force, it is the same, okay, they will be the same. So this gives us the stress. There are different types of stress: tensile, compressional, which is longitudinal, bulk or volumetric stress, which is related to volume, and here we are interested in this, okay, the bending angle, sliding stress, okay, which causes sliding of one face over the other. Similarly, here strain can be categorized into different types. Strain is the change in dimension to the original dimension, okay. So the dimension can be length, it can be volume, it can be angle. So here there are different types of strain: longitudinal strain for length, volumetric strain for volume, shearing strain for angle. So tangential stress is basically the reaction, the internal reaction to the externally applied force which acts parallel to the surface, okay, parallel to the surface. Let's say this surface has a cross-sectional area A, these two surfaces. The externally applied force acts parallel, and this causes sliding of one face over the other, okay, and this causes bending of the material, and this bending angle is the resultant strain, this bending angle. And we are interested to establish a relationship between this, stress, externally applied stress, and the bending angle, the extent of the bending angle. So here the shear strain is basically the tan of this bending angle, okay. So the relationship between this tangential stress or shear stress, tangential stress is also called as shear stress or shearing stress, okay. Shearing or tangential stress, they are the same. So the relationship between tangential or shearing stress and shear strain, that is called as modulus of rigidity, okay. So let us say we have a object, okay, it has a certain cross-sectional area, uniform cross-sectional area on each side. So we have an externally applied force which acts parallel to the surface of cross-sectional area A. This causes bending of one face over the other. The lower face is fixed, the upper face is movable. For simpler analysis, I am considering this. So this face bends by an angle theta, okay, it bends by an angle theta. So here the tan of this angle, that gives us the shearing strain. So let's say this movable face, it moved by a margin of delta L, okay, let's say it moved by a margin of delta L, and the length of this face, as we are considering uniform dimension, the length of this face, let's say it is L. So here tan theta is delta L by L. Don't confuse it with longitudinal strain, okay, don't confuse it with longitudinal strain, it is different. Here delta L is the extent of bending, the distance by which this point has moved to the right, Okay, this is not increase in length. Okay, don't confuse it with longitudinal strain. It is not longitudinal strain, delta L by L. Don't confuse it with that. I'm again, telling you. So this is the extent to which this fixed point, initially fixed point, has moved to the right in response to the shearing stress, the shearing force. So here tan theta, which is the shearing strain, that is equal to delta L by L. Now as this angle is very small, it is generally very small, so it is nearly equal to theta, which is equal to delta L by L. So the shearing strain tan theta is equal to theta, which is equal to delta L by L. So Hooke's law, which is basically the relationship between stress and strain, stress and by strain relationship, here modulus of rigidity establishes a relationship between tangential stress and tangential strain. So within the elastic limit, the tangential or shearing stress is directly proportional to the tangential or shear strain. Whenever you hear shearing strain, it means the same as tangential. Tangential and shear, they are the same. So tangential or shear stress is directly proportional to tangential or shear strain. That is, the bending of the object is directly proportional to the applied bending force. Bending angle is directly proportional to bending force. When the bending force increases, bending angle increases. That is basically Hooke's law applied to bending of materials, which basically gives us the modulus of rigidity. So sigma theta is directly proportional to epsilon theta. This is the shearing stress or tangential stress, and this is shear strain. Okay, and the ratio of tangential stress to tangential strain, that is rigidity modulus. Sigma theta by eta theta, this gives us the rigidity modulus. Okay, so this. Now here the tangential or shear stress is basically force by area. Force by area. Okay, this is the tangential stress. And the tangential strain or shearing strain is the tan of this angle, the bending angle tan theta. Okay, F by A, shearing stress, shearing strain tan theta. So this ratio, tangential stress by tangential strain, this will be equal to this. The rigidity modulus constant, the rigidity modulus eta, that is equal to F by A, which is tangential stress, and tan theta, which is tangential strain. Tan theta is nearly equal to theta, so F by A by theta. Okay, now here we have determined the value of tan theta, which is equal to delta L by L. So if we substitute that value, we will get here this rigidity modulus eta is equal to F by A theta or FL by A delta L. Okay, as this theta is equal to delta L by L. So L goes to the numerator, delta L remains in the denominator. This is the formula of modulus of rigidity. Again, as you can see here, it has a value of Newton per meter square, and here the constant, it depends on various physical and chemical characteristics of the material. Okay, and here as you can see, L by delta L, it has the same units. L by delta L, it has the same units, so they cancel out each other in terms of units, and we are only left with F by A. That's why the unit Newton per meter square. And here are some commonly used materials with their rigidity modulus values, again in terms of 10 to the power 9 Newton per meter square. Aluminium, it is 25, that is 25 into 10 to the power 9 Newton per meter square. Copper, it's 42. Iron, it's 70. Steel, 84. Wood, 10. Glass, 23. Okay, and we have nickel, which is equal to 77. Again, these are rough approximate values. There will be some margin of error, some plus minus, but these are the rough approximate values. Again, whenever you use a particular material, you have to be careful about the rigidity modulus. Whenever it's a specific application, for purpose of specified use. So it will always be there in the specification sheet. Now, a proper combination of all the modulus of elasticity, that is Young's modulus, bulk modulus, and rigidity modulus, that is required for any design purpose. A proper combination of all three parameters: length, volume, bending angle. All three should be properly calibrated, should be properly, measured, properly tested for any design purpose. Okay, so we have to take into account all three parameters. So we have discussed Young's modulus elasticity for length, bulk modulus of elasticity for volume, rigidity modulus or shear modulus for bending angle. Okay, so here we have discussed. Okay,